Okay, guys. So we ended up in the last video sort of seeing where the Nernst equation comes from and how it lets us measure these standard reduction potentials and determine whether a given redox couple is going to be strongly oxidizing or strongly reducing relative to the the standard hydrogen electrode. Right now, there's one additional little wrinkle here we got to think about, and that has to do with pH. Because if you remember, with respect to standard state free energy values for chemical reactions, the way we've been talking about them before, um, the biochemists always reference this um, at pH 7 relative to those other conditions for measuring standard states. And so we have to think about this delta G naught prime, right? For the way in which biochemists tend to want to think about standard state free energy values versus chemists, right? We're always thinking about this at pH 7. And so our standard state free energy values get this additional little prime to remind us that that's standard state conditions at pH 7. Well, something analogous also happens when biochemists think about redox reactions. They want to do basically exactly the same thing. And the analogy here again is, if we're think about these sort of standard free energy values at pH 7, we got to think about reduction potentials at pH 7 too. So again, the analogy would be, if we're thinking a standard reduction potential for a given redox couple under a sort of normal standard conditions, you don't worry about so much at pH. Biochemists, however, are going to want to worry about pH, and so we're going to think about standard reduction potentials at pH 7, and we do the same basic thing. It also sort of gets the prime. But the thing to remember here is that the measurement of these standard reduction potentials at pH 7, what's at pH 7 is the what's in the test cell, right? So the test cell reaction is at pH 7, right? But what's not at pH 7 is the standard hydrogen ion electrode, right? So these sort of standard reduction potentials, or epsilon not prime values, these are still referenced to the standard, standard hydrogen electrode at sort of 1 molar proton, 1 atmosphere hydrogen gas, right? So the reference when you see these standard reduction potentials at pH 7 is only referenced at pH 7 to the test cell reaction, right? And actually, it turns out you could take a standard hydrogen electrode that was, at 1 atmosphere hydrogen and everything else, and adjust the pH to 7. And what you find, it relative to the standard electrode, it has a reduction potential of minus 0.42 volts, right? pH 7 versus at 1 molar. So just one thing to keep in mind. We again have these standard potential values, just like with free energies, reference to pH 7 when you're thinking about these reactions in a biochemical context. Okay, so let's an example. How do you use some of this, right? All right, so imagine for a second a reaction we've talked about a little bit before. Let's say we've got the reduction of ethanol plus NAD plus, right, to acetaldehyde plus NADH plus proton, all right? Of course, this is the alcohol dehydrogenase reaction, not running in the direction of the fermentation reaction, but now running the way it does in your liver on a Friday or Saturday night, for example, right? And the question is, can we use standard reduction potentials to figure out the standard state free energy for this reaction running this direction? And the answer is, yeah, absolutely we can. But what we have to do is kind of what we did at the very beginning of the class, thinking about free energies for half reactions. We have to decompose this into a couple of half reactions for which we have some measured standard state reduction potentials. And that's relatively straightforward, right? So we do that. The two half reactions would be, in this case, NAD plus, right, plus proton, plus 2 electrons, right? So this is the standard reduction potential half reaction for NAD plus to NADH. And that standard reduction potential at pH 7 is equal to minus 0.320 volts. Okay. Okay, well, we can do something similar in terms of the ethanol acetaldehyde half reaction. Say, okay, well, acetaldehyde, right, plus, oops, plus 2 protons, plus 2 electrons, right, would then give us ethanol. And the standard reduction potential at pH 7 for that redox reaction is minus 0.197 volts, okay? But to use this, right, one of these we got to flip this around, right? The NAD reaction, that's running the right direction we want relative to the reaction up here we're thinking about, right? Which is the oxidation of ethanol to acetaldehyde, right? All right, by NAD plus. That's running the right way. But the acetaldehyde ethanol reaction, it's reversed, right? So it's the same game we played before, which is you got to flip that around, but you got to remember when you do flip it around to also change the sign of the standard reduction potential, because we're going to essentially invert it. So if you do that, right, and you flip this guy around, you would change this one now to sort of ethanol, right? Goes to acetaldehyde. Plus 2 protons, plus 2 electrons. Standard reduction potential in that direction, of course, is now plus 0.197 volts, right? The change in the standard reduction potential now, you basically just add these guys up, right? So you would add up the one going in the half reactions that balance to the overall reaction that we want, which would be this guy and this guy, right? You do that, that's difference in the standard reduction potentials is just going to be minus 0.320 volts plus 0.197 volts, which is just going to be equal to, minus 0.123 volts, right? So that's great, right? So, and in general, I mean, the difference in the standard state reduction potential, one could express as simply being equal to the reduction potential, measured reduction potential of the acceptor, right, minus the reduction potential, right, of the donor, right? Sort of in the general sense. Okay, but again, the idea here is we're trying to figure out how this relates to free energy values. Well, again, if you remember that definition that we started out with, or that we came to in terms of the standard state reduction potential, remember this? We defined it because of that relationship between free energy and electrical work under the conditions that we sort of went through that constraint of the Gibbs equation. That's just equal to minus delta G naught prime divided by NF, right? Remember, if all we're worrying about is electrical work, we're not letting anything else happen, the free energy difference divided by the charge on the particle times Faraday's constant is equal to the standard state reduction potential. Well, that's kind of cool, because what that means is now this delta epsilon naught prime is simply equal to delta G naught prime, right? Divided by NF, right? Minus delta G naught prime divided by NF, right? That's kind of amazing, right? Because if that's the case, what that means is that the standard state reduction potential difference is simply equal to the delta delta G not prime divided by NF in this expression. But we don't have to think about those delta delta G's, right? Because remember, when we talked about that original derivation, when I first went through this sort of that electrical work, that's defined with reference to moving that particle, say, from an infinite distance to a particular point in an electrostatic field. Or in other words, these standard state reduction potentials are all referenced to zero, right? When you think about, or the free energy difference is referenced to a value of zero. That's also inherent in the way we talked about the standard reduction, the standard hydrogen electrode, right? So if these delta G values are all relative, say, to a zero reference, right? That delta delta G we can dispense with because we're both subtracting two numbers that were both differences relative to zero. So that really is just equal to delta G naught prime divided by NF, which is fantastic, right, in general, because what that means is by knowing the standard state reduction potential, by knowing the charge on our particle, which in course, in this case would be an electron, right, all we have to do is rearrange that relationship and we can solve for these free energy values quite simply. So that delta G naught prime is simply equal to standard state reduction potential. Let me write this out a slightly different way. All right, if we go back to this again, where prime is simply equal to delta G naught prime, again, we can write it this way instead of as a delta delta G because of that reference that I just mentioned. Delta G naught prime divided by NF, so that the delta G naught prime is simply equal to the difference in the standard state reduction potential times NF, right? And in the case of that, the ethanol reaction that we just did a minute ago, this, I'll just write it out again. Ethanol plus NAD plus goes to acetaldehyde plus NADH plus proton. The free energy difference in this reaction, this redox reaction, is just equal to minus NF times the difference in the standard state reduction potential, which is just now equal to minus 2, because we had 2 electrons, right, times 96.5, and adjusted for the units, which I'm not going to write out here explicitly, times minus 0.123 volts, right? We end up with plus, in this case, 23.74 kilojoules per mole. If you go through the units, right? And you carry everything through, right? Pretty cool, right? All right. So now we can go back to NADH for a second, right? And that sort of whole question of why does NADH inherently have so much potential energy that's useful for making ATP? Well, let's write that out, right? So we could say, well, get this NAD plus reaction, or the reduction of NAD plus to NADH. And we know the standard state reduction potential for that, pH 7, is just equal to minus 0.320 volts, right? And the other reaction we'd need, because ultimately where we're going to take these electrons, we're going to dump them, is into oxygen. So we need a reaction that looks something like this. 1/2 O2 plus 2 protons plus 2 electrons goes to water. with a standard reduction potential, in this case, of plus 0.815 volts relative to the standard hydrogen electrode, right? So now, if you flip these reactions around appropriately and you write the overall reaction out correctly, you end up with something that's this, NADH, right? Of course, remember here, you've got to invert this guy, right? You do that and you write this out, you get a reaction H plus 1/2 O2 goes to NAD plus H2O. And if you calculate the standard reduction potential you get out of this, you flip the sign around here, right? I'm sorry, shoot, didn't mean to do that. Minus, you flip that sign there, add these two values up, you end up with a standard reduction potential. Shoot, our standard reduction potential difference. That equals 1.14 volt. If you now take that value for the standard reduction potential, right, and you substitute that into the expression we just talked about here, right? So you now take this, you take, well, what is the free energy difference for that value of a difference in standard reduction potential? What you find is that the delta G naught prime for oxidation of NADH to with water and a proton, with oxygen, molecular oxygen and a proton, serving as the oxidant for reduced NADH, is a free energy value of minus 220 kilojoules per mole. So that's where that free energy value comes from, and it has everything to do, the question I posed at the beginning of this lecture, it has everything to do with the ability of oxygen, molecular oxygen, to serve as a fantastic and deep oxidizing sink relative to the tendency of those electrons in that nicotinamide ring to want to be ejected or released by NADH, so it can go back to NAD plus, and the ability of those electrons to then flow into molecular oxygen to form water. And the free energy difference available in that electron flow gives us the energy we need to synthesize a whole lot of ATP. And we'll start talking about that next time.